Alrighty, folks, so let's move now on to the second last lesson of Math 30-1, Hard to Believe, okay? This Unit 5, Lesson 2, Combinations. In the previous lesson, we talked about permutations. We're still going to be thinking about them. They will come up today or in this lesson as well, but we're going to focus primarily on these combinations, the combs part of perms and coms, okay? So as always, here are the big ideas, the main skills, the main questions we're hoping to be able to answer after this lesson. So you can kind of use this as a little checklist to check in with yourself at the end, right? What are you feeling pretty good about? What do you maybe need a little more practice with and or need to reach out to me about? But without further ado, let's jump in. What is a combination and how does it compare to a permutation? What's the difference? Well, to think about the difference between a combination and a permutation, let's just kind of see the logic here. In everyday life, right, we use that word combination pretty loosely, okay, without thinking about whether or not order matters. So, for example, you might hear, this smoothie is a combination of 3 ingredients, right? That sounds totally right. Nothing wrong with saying that. The order, think about it, right? The order doesn't matter for a smoothie. Whichever order we choose the 3 ingredients, the smoothie is the same if the 3 ingredients are the same, right? For example, if I make a smoothie and I put in orange juice, then a banana, then strawberry, and I blend it all up, I'm getting the same smoothie as if I did banana, then strawberry, then orange juice, right? It's still the same smoothie. So order that I choose them doesn't really matter. Choosing the same things in a different order still gives us the same outcome in the end, right? But another way you might hear it in your day-to-day is something like the combination to my locker is, 12, 24, 30. Now, order does matter here, right? Because 24, 12, 30 or 30, 12, 24, even those are the same 3 numbers, they're in a different order. And so they will not open up the locker, right? The same 3 numbers in a different order is actually a different outcome. It's a different code, a different combination. So it actually means it's not a combination at all. This would be an example where we would need to think about permutations. Okay, so in math, we therefore use more specific language to avoid confusion here, right? So again, we use that word combination. I might even sometimes say, well, we're combining stuff when I'm really thinking about order mattering, right? It's easy to slip up because our everyday lingo can slip into our math a little bit, okay? But important to always think, does order matter here or not? If so, if it does matter, we're dealing with a permutation, right? Meaning that the same things but arranged differently is considered a different result, right? So even if all the same stuff is there but it's arranged in a different way, that's a different outcome if order matters. And we're dealing with a permutation. In a combination, order does not matter, meaning that the same things but arranged differently is still considered the same result, right? So again, orange juice, banana, strawberry smoothie is the same result as a banana, strawberry, orange juice smoothie. Same 3 things, doesn't really matter that the order is different for a situation like this. Combination to a locker, the order gives us something completely different, right? The code to a locker is actually, it's more like a permutation, right? Because 24, 12, 30, even though that's the same 3 numbers, arranged differently, that's a different code. That is a different outcome, right? So let's try some examples here, thinking about, is this a permutation or is it a combination? Because that's always going to be kind of one of the very first things we need to think about with these is, does order matter or not? So it wants us to state whether each situation would be one where we would need to think about perms or coms, okay? So choosing a team of 2 people from a group of 10. So choosing a team of 2 people. So think about it this way, right? If we choose the same 2 people in a different order, have we made a different team of people? Like if I pick Alice and Bob, is that the same team as if I pick Bob and Alice? Well, yeah, right? It's still the same team. It's the same 2 people. They're a team, implying that they have like equal power, right? They're just a team. So it doesn't seem like order makes a difference here. The same 2 people chosen in a different order still makes the same team in the end, right? So that's a combination. What about this one? Choosing a president and a vice president from a group of 10. Now, does order matter? If I pick two people to be one to be president and one to be vice president, and then I switch the order that I picked them, does that give us a different outcome? Well, then it does, right? I'll stick with Alice and Bob. If I make Alice president and Bob vice president, that's a different outcome than if Bob is president and Alice is vice president, right? So order does matter there. That's a permutation. The same things, but in a different order, the same things arranged differently, is actually a different outcome, right? President and vice president would be switched around. Order matters there. That's a permutation, right? Making a list of your top 3 favorite books. So a list of your top 3 favorite books. So my third favorite book is this, my second favorite book is this, and my first favorite book is this. Does order matter there? If I pick the same 3 books, but I list them in a different order, do we still have the same outcome? No, we don't, right? Because we're listing, this is my first favorite, my second, and my third favorite, right? And so switching those around gives us a different list. You actually do have a different, favorite book and a different second favorite book. So that is also a permutation. The same 3 books arranged differently makes a different top 3 list. Order matters. Okay, choosing 3 books to bring on vacation with you. So now we're just picking 3 books, we're going to bring them on vacation. So if I choose, 3 books, and those are going on vacation with me. If I change the order that they were chosen, do I have a different outcome? Do I have a different set of books being brought with me? No, right? Order doesn't actually make a difference there. Either way, the 3 books are coming on vacation with me. So there might be different ways to choose the 3 books. I might choose those 3 books or a different 3 books, but choosing the same 3 books in a different order doesn't give us a different outcome. So that is a combination, okay? Makes sense, right? A good way to test is to ask yourself, if I have all the same stuff, but I arranged it differently, is that actually a different outcome, right? For a team of 2 people, no. Either way, you made the same team of the same 2 people. For a president and vice president, well, that's different, because now whoever was president would become vice president if we switched it around, and vice versa, okay? All right, let's take a look at the formula behind combinations. So, the formulas for both perms and coms, which are both on your formula sheet, okay, are, we saw this one yesterday, n pick r, or n permute r, is just n factorial, the number of ways to arrange n things, divided by n minus r factorial. Remember, this is just the number of ways there are to the number of ways to arrange the things that were not chosen, right? We're choosing r things from n options. So n minus r just tells us how many ways are there to arrange the leftovers, the things we didn't choose. We want to divide those out because we don't care about their order. We care about how many ways are there to arrange the things that were chosen. Okay, so that's why we divide them out. Now, this combinations formula, you can see it's very similar, but there's an extra r factorial in there that we're dividing by. That actually makes a ton of sense. We'll take a look at it in some more depth, but even intuitively, right? This is the number of ways to arrange the things that weren't chosen. Obviously, we still don't care about that. We're not choosing them. But also now we're dividing by the number of ways to arrange the things that are chosen. Well, remember, for a combination, we don't care about arrangements. We don't care about the different ways to arrange the same objects once chosen. We just care about how many different ways there are to choose them in the first place. So we actually do want to divide out the orderings, the different arrangements of the things that were chosen as well. We'll examine that in some more detail here in a second. Okay. Now, just a heads up, this is sometimes also written as this. So like, for example, if I were choosing, and I didn't care about order, 3 things from 5 options, it could actually also just be written as 5, 3, almost like a fraction, but without that. That's just recognized to mean 5 choose 3, 5 combine 3, okay? That's what that means there. So for each of these, n means the same thing, r means the same thing as it did in the previous lesson. N is the total number of options, the things there are to choose from, while r is the number of things that we actually choose from that group, okay? So NPR tells us how many different ways we can choose r things from a group of n things if order does matter, right? If we choose the same things and arrange them differently, and that constitutes a different outcome, then we're dealing with NPR. If we choose the same things and arrange them differently, and that's not considered a different outcome, like choosing 3 books to bring on a vacation with us, for example, okay, then that's what NCR tells us, and choose R. It tells us how many different ways we can choose R things from a group of N things if order does not matter. And so in the previous lesson, right, we saw why the formula for perms makes sense. NPR is equal to N factorial. Well, there's N factorial ways to arrange N things, but if we only choose R things out of those N options, we don't care about the order in which the unselected things are arranged. And so since N minus R things are not chosen, we divide out the number of ways there are to arrange these things, which is just N minus R factorial. Okay. When we examine the formula for combinations, similar logic, we already kind of touched on it, okay? We can see that it also makes sense though. So N choose R, we sometimes say, is N factorial, still dividing out by N minus R factorial. Okay, again, there are N factorial ways to arrange the N things. We don't care about the unselected things, so we divide out N minus R factorial like we did with permutations, right? We still don't care about the order of them, okay? But now we also don't care about the order of the things we did select. So we don't care about how many ways there are to arrange the R things that were chosen either. And that's why we're going to divide the different arrangements of R out of the total number of ways to arrange as well. What we're interested in is just how many different ways could we choose R things from N options? How many different groups could we make? But we're not worried about the orders within those groups, right? So we also divide out the ways there are to arrange the R chosen things. And how many ways are there to arrange R things? R factorial, okay? Let's just take a look at an example here, kind of thinking about this a little bit. So suppose that you had to choose 3 letters from a group of 4, okay? And the 4 letters we have to choose from are A, B, C, D. Here are all of the possible permutations, okay, where order would matter. So you can see, right, well, one option for what we could choose in the first place is A, B, C, right? So choosing A, B, and C, if we think about all the different permutations, here they are. We could do ABC, ACB, BAC, BCA, CAB, CBA, right? But we could also choose, in the first place, we could have picked A, B, and D. And then we could have arranged them all these different ways, okay? Or A, C, and D, and arranged them. Or B, C, and D, and arranged them in all those different ways. So think about this. Within each grouping, right? So ABC, ABD, ACD, and BCD, there's going to be, for all 4 of those different possibilities for how we could have chosen the letters, there's 3 letters, so they could be grouped in, or arranged, in 3 factorial ways, which is 6, right? That's exactly what we see here. If we pick ABC, there's then 6 ways to arrange just those, and 6 ways to arrange ABD, and 6 ways to arrange ACD, and 6 for BCD, okay? So there's 6 ways to arrange the 3 chosen letters. But now, for a combination where order doesn't matter, all 6 of these within that group are identical, right? If we don't care about the order they're arranged in, then all 6 of these are the same thing. They all have the same 3 parts. If order doesn't matter, these are not different outcomes. They're all the same thing. They're just ABC, okay? All that matters for a combination is which 3 letters were chosen. So that means that we really only have 4 unique outcomes if order is not important, right? It's ABC arranged however, ABD arranged however, ACD arranged however, and BCD arranged however. Those are all just one outcome in that case. Meaning that, how many times too many arrangements do we have? Well, 3 factorial times too many, right? Because we took our 4 different ways to choose the letter, and then we're kind of multiplying it by 3 factorial, right? We're getting 6 here, 6 here, 6 here, and 6 here. So we're taking 4 times 6. So that's 3 factorial times too many arrangements considered. How do we fix that? Well, we're multiplying by 3 factorial when we don't want to if order doesn't matter. So to undo that, divide by 3 factorial. And that's exactly why you see this dividing by r factorial there. If we don't care about the order of the r things that were chosen, we just need to divide it out of the normal permutation formula, right? This assumes that the order of the r things does matter. If it doesn't, just divide it out. We don't want to multiply by the number of different arrangements for the things that were chosen in a combination. So evaluating each situation, just to put these formulas to the test, where order does or does not matter using the formulas, right? If order does matter, we do n pick r, npr, 4 factorial, n factorial, over n minus r factorial, right? Doing 4 factorial over 1 factorial, we don't care about the order of the one thing that we didn't choose, okay? Gives us 4 factorial, which is 24. Hey, 4 times 6, right? 4 different ways to choose the 3 letters, but for each of those, 6 ways to arrange them. 4 times 6 gives us 24, okay? Now, this one, look what it gives us, right? 4 factorial, divide by the number of ways to arrange the things that aren't chosen, but also divide by the number of ways to arrange the things that are chosen because we don't care about them, right? We don't want to multiply our 4 ways to choose the letters by 6 factorial because these don't count as different outcomes if order doesn't matter. And sure enough, it gives us exactly what we saw, 4, right? 1, 2, 3, 4 different outcomes if order doesn't matter, just choosing the different letters. And so the steps for using NCR on your calculator are very similar to what we were doing in the previous lesson for NPR and factorial. You'll find it in the same place. So first, enter N, the number of things there are to choose from. Press Math, okay? At the top, move all the way right to Probability or PRB. Press option 3. That's the one step that's different. Before you were pressing in the previous lesson, we would press option 2 for NPR. Now we're going to press option 3 for NCR. And then finally, you enter R, the number of things that will be chosen, right? So you can think of it like you're putting in your N, you're telling it you want combinations, and then you're telling it what R is, right? Read it left to right, and that's the order of the buttons you press. Put in your N, go to Math to find choose or combinations, and then put in your R. I'll walk you through the steps here on the calculator really quick. So suppose we were wanting to do that example we just did, right? How many ways are there to choose 3 letters from 4 options, A, B, C, D? We could go, well, we want to do 4, C, 3, right? 4, choose 3, so we would go 4. Then we would press Math all the way over to Prob or PRB, and then see it there, option 3, NCR. So option 3, I've got 4, choose 3. Again, yours might look a little bit different. I know on my calculator that I really use, it's an older one, it just says NCR. It doesn't do the little like 4 as a subscript and then the 3 as a subscript, but it works the same way. Okay, then we would hit enter, and hey, that's the answer we got by thinking about it as well, 4. So let's try out some examples. A 4-person math teacher committee is going to be formed at a school with 10 math teachers. The number of different committees that could be formed is, okay. So thinking about this, right, does order matter for a committee? Well, no, right? If we choose 4 people, they're on the committee. Doesn't really matter what order we choose them. They're all on this committee, right? A committee's like a team, basically. So we're going to use combinations, C, right? Order doesn't matter. The same people chosen in a different order still makes the same committee at the end of the day. Okay, now we're going to choose a 4-person committee from 10 teachers. So that means this is our R, that's how many we're actually going to choose, and this is our N, right? How many options do we have? So again, we could just say 10, whoops, it's 10, choose 4, right? And if we go to our calculator and we do that, if we go 10, math, probability, choose 4, it's telling us that there are 210 different ways the committee could be arranged, or chosen, I should say. Not arranged. Arranged was definitely the wrong word to use there. Okay, if we want to get some comfort with the formula, let's try that out as well. So 10 choose 4 is, well, here, let me just write the general formula off to the side here. N choose R is n factorial, divide by the number of ways to arrange the things that aren't chosen, and also the ways to arrange the things that are chosen, because we don't care about those arrangements now that order doesn't matter. So this will be n is 10, so 10 factorial, over 10 minus 4 factorial times 4 factorial, giving us 10 factorial over 6 factorial times 4 factorial, right? 10 minus 4 is 6. That represents the ways to arrange the 6 teachers who aren't chosen, which we definitely don't care about here. That gives us 10 factorial is 3,628,800. Got that from the calculator. Divided by 6 factorial is 720, and 4 factorial is 24. So dividing that by 720 times 24, we get 210. Same result, right? And so that's what that 10 choose 4, function on your calculator is doing. So good to understand what the formula is behind, the magic of your calculator, okay? And even better to understand why this formula makes sense. How many ways are there to arrange 10 things? But we don't care about the order of the things that aren't chosen. And since it's a committee, we also don't care about the order of the things that are chosen. We just care about how many different ways there are to take 4 things from 10 options, but not the ways to arrange the 4 things that are chosen. Okay, let's try this one out. So a student who loves comic books wants to build a superhero dream team of 5 members using the original members of 3 comic book teams. They are going to choose from the Avengers, who had 6 superheroes on that team originally, the X-Men, who had 5 on that team, and the Justice League, which was 7 originally. Okay, it's asking us how many different teams are possible. So let's think about this. Well, how many options do we have to choose from to make our dream team of 5 members? We've got 6 Avengers, 5 X-Men, and 7 Justice League members, right? So our N, the options we have to choose from, is going to be, 6. I'll just do 6 Avengers, right? 5 X-Men. So 5 X-Men. And 7 from the Justice League. So 7 from the Justice League. So plus 7. Okay? Meaning that the total number of superheroes we have to choose from is 18. How many of those are we going to choose? Well, we're making a dream team that consists of 5 members. So we're choosing 5 different superheroes from 18 options total and trying to figure out, okay, how many different teams could we make? Now, does order matter here? Well, no, right? Like if we choose, I don't know, Batman, Superman, and Iron Man, it's the same team as if we pick Iron Man, Superman, Batman, right? It's still the same team. It's made of the same people. The order we choose them doesn't give us a different team if we choose the same people, okay? So we are going to use combinations here. So we've just got 18, choose 5. 18 combining 5. Okay, how many ways are there to combine 5 different things chosen from 18 options if we don't care about order? So 18 choose 5, if we go to the calculator and put that in, 18 and then math and then over to probability and option 3, NCR, we get that 18 choose 5 is 8,568. Again, could use the formula there, but that's the result we get. Okay, now some restrictions or some conditions. How many different teams are possible if the team must include Iron Man, who is an Avenger? Okay, so like we did with permutations, think about the restrictions or the conditions first, right? So all that's really happening here is just that one choice has been made for us, right? That's one way to look at it. We want to put 5 members onto a team, but they've already given us one person who has to be on that team, and it's Iron Man. So really, we just have 4 people left to choose, right? One spot is already filled. So really, I'll just say one spot already filled. One spot already filled. So we're really just choosing 4 team members from how many options? Do we still have 18 to choose from? No, right. We actually only have 17 to choose from because Iron Man's already been chosen, right? So there's 17 superheroes to choose from who aren't Iron Man, and that's what's left for us to work with. So we're really just choosing 4 team members from 17 options, right? Iron Man's already chosen. That's done. So what we're really being asked here then is how many ways are there to choose 4 from the remaining 17? That just gives us 17 choose 4, which comes out to 2,380, right? That's not that surprising. That just represents, right, all of the ways that Iron Man could have been part of one of these teams, right? How many different teams are possible if the team cannot include Batman, who is a member of the Justice League? Okay, so now we're not allowed to pick Batman. So how many members are we choosing? We're still choosing 5, right? How many options do we have? Now we only have 17, right? Batman has been taken off the table. We're not allowed to pick Batman. So that just means, right, we're still choosing 5. It's just that we're not allowed to use all 18 options. Still choosing 5 members. But now we only have, now from only 17 options, because we're not allowed to include Batman. So that means we're going to have 17 choose 5. So 17 choose 5 gives us 6,188. You might notice if we added these two together, right, we would get 8,568, which actually makes a lot of sense. The number of ways to include one superhero, right, is going to be, well, take the total and subtract the number of ways where one is not included, right? If you switch this to Iron Man, you can kind of see that all this represents is all the different teams that include Iron Man. So if we added all the teams that didn't include Iron Man, I know it's Batman here, but it would be the same math involved, right? You should get the total number of ways to choose 5 teams. All the ones that do include Iron Man plus all the ones that don't include Iron Man gives you the total number of ways to choose the team. Okay, so there we go. There are 6,188 ways to make the team if we cannot include Batman. Okay, let's think about something here. So as is often the case with this stuff, it's often nice to think about it with an example to kind of ease ourselves into the logic here. So it says, how many ways are there to form a committee from 5 teachers and 15 students if the committee must consist of 2 teachers and 3 students? So we're kind of making 2 separate decisions here, right? Yes, we have 20 people overall, but we're not allowed to just pick 5 of them at, random. We have to include a certain number of teachers and we have to include a certain number of students. So this is really just 2 separate choices to make, right? What are we doing? We're choosing 2 teachers from 5 options, which would be 5 choose 2. That's the number of ways to just choose the teachers, right? But then we're also choosing 3 students from 15 options, which would just be 15 choose 3, right? So we're looking at the number of ways we could choose 2 teachers out of 5 options and the number of ways we could choose 3 students out of 15 options. Now, 5 choose 2 is 10, and 15 choose 3 is 105, meaning that to pick our 2 teachers, there's 10 ways we could do that, right? And to choose our 3 students, there's 105 different ways we could choose them. So there's 10 different ways to choose the teachers, and there's 105 different ways to choose the students. Now, what can we apply here? Remember, if there are P ways to do one thing and Q ways to do another thing, then there are P times Q ways to do both things, right? That's what the fundamental counting principle tells us. So we can apply the fundamental counting principle here. If there's P ways to do one thing and Q ways to do another, there are P times Q ways to do both things. And the logic makes sense here, right? Why multiply them together? Well, because for each of the 10 ways to choose the teachers, right, there's then 105 different ways we could choose the students. So for every single way this could turn out, there's 105 different ways this could turn out. So we have to multiply this by 105 to figure out the total number of ways that both of those things could happen. And that's what we're doing by forming the committee. We're doing both of these things. We're choosing 2 teachers from 5 options and 3 students from 15 options. For each of the 10 ways to choose the teachers, there are 105 ways to choose the students, so we need to multiply them. There are 10 times 105, or 1,050 ways to form the committee. Okay, let's see if we can apply this idea here in an extension of that superhero example. All right, so same student, same situation. They want to make a 5-member team out of the Avengers, the X-Men, and the Justice League. How many different teams are possible if the team must include 3 X-Men and 2 members of the Justice League? Okay, so we need to have 3 X-Men and 2 members of the Justice League. So do you see how this is kind of like making 2 separate decisions, right? We've got to choose 3 X-Men from 5 options, and then we've got to choose 2 Justice League members from 7 options, right? And then we've got to multiply those together because, again, if I do the X-Men here, don't always have to split it up like this, but for our first example, I might, just to really illustrate the thought process. We have to choose 3 X-Men, we have 5 options. So how many ways are there to do that? Just to choose our X-Men? Well, 5 choose 3, right? Giving us 10 total ways we could just choose the X-Men. Now for the Justice League, I'll just say JL for short, okay, there's 7 we could choose, and we're going to have to pick 2 of them. 7 choose 2, we put that in the calculator, gives us 21, right? Now again, think about this. There are 10 ways to choose the X-Men, but for each of those, there's 21 different ways we could choose the Justice League members that are left to choose, right? So overall, for every single one of those 10, there's 21 different ways we could do it, so 10 times 21, right? Or 210, okay? So the total number of ways, like I said, it's just going to be 5 choose 3 times 7 choose 2, giving us, like we have already calculated, 10 times 21, or 210 different teams that satisfy these conditions, right? There are 210 different ways to make this team if it has to have 3 X-Men and 2 members of the Justice League. All right, what about if the team must include 2 Avengers? So there are 6 choose 2 ways to choose the 2 Avengers, right? Avengers, I'll just say A for short, 6 choose 2, okay? What about the 2 X-Men? Well, there's 5 X-Men, and we're choosing 2 of them. So 5 choose 2. And then the Justice League, there are 7 of them, and we're choosing only 1, right? So again, we could calculate this out. 6 choose 2 is 15. 5 choose 2 is 10. Do you notice something here? This is an interesting observation. The ways to choose 3 things from 5 options is 10. Same with when we want to choose 2 things from 5 options. It's also 10. That actually makes a ton of sense when we think about it, right? Because since order doesn't matter here, choosing 3 things is actually the same as, choosing 2 things. Look at it this way. If you choose 3, then you haven't chose 2, right? So asking how many ways are there to choose 3 things out of 5 options is kind of like asking how many ways are there to not choose 2 things, right? And that's why these are always, like these complementary ones always give the same number, because we could look at it as we're choosing the 3, but that's also saying we're leaving behind 2. So not unsurprisingly, the numbers come out to be the same, right? Choosing 3 is also just looking at how many different ways are there to leave 2 behind, right? And so we get the same result when we say how many ways are there to choose 2 out of 5, right? Okay, anyway, 7 choose 1. This isn't very surprising. There are 7 ways to choose 1 thing from 7 options, right? Extending that to what we were just talking about, there's also going to be 7 ways to choose 6 things from 7 options, right? 7 different ways to do it, meaning there's 7 different people that could not be chosen, right? You're choosing 6 of them, so there's only 1 to not be chosen. Anyway, getting back to it here, okay, so how many ways are there total? Well, we have to multiply these together by the fundamental counting principle, right? There's 15 ways to choose the Avenger, but for each of those, there's 10 ways we could choose the X-Men. So multiply those together. And then for all of those different outcomes, there's 7 ways we could finish it off with a member of the Justice League. So we're going to have to multiply all those by 7, right? 1 for each different member of the Justice League. So we're going to have, 6 choose 2 times 5 choose 2 times 7 choose 1. Or 15, since we already calculated them, times 10 times 7. So that's 150 times 7, which gives us 1,050 possible teams that satisfy these conditions. So there's 1,050 different ways to make this 5-member team if you've got to have 2 Avengers, 2 X-Men, and 1 member of the Justice League. Cool, right? Pretty powerful calculation, something that kind of makes your head spin at first, hard to think about. But by using these, mathematical principles involved, we can get there a lot quicker than just trying to list out all the different teams. It would take forever to list out all 1,050 options. Okay, so go ahead and try this one out. Okay, part A, part B. As always, feel free to pause and try a couple more and get comfortable with it, but at least try this one while it's fresh in your brain. And then when you come back, we'll talk about what to do when there is more than one way to satisfy the conditions. So sometimes there is more than one way to meet the conditions that we've been given. Okay, might be multiple cases that could satisfy our conditions. So how do we deal with that, right? In order to do it, we're going to have to add up all of the possible ways that each case could be selected in order to find the total number of outcomes. So when would this happen? When would we have multiple cases that could satisfy? One of the big places it pops up is when the words at least or at most are used, right? Best way, I think, to think about it is probably just to start out with an example so we can see the logic here. So consider this one. 5 students in grades 11 and 12 are to be chosen to represent Argyle at a math competition. Okay, there are 20 grade 12 students and 15 grade 11 students to choose from. The group must contain at least 3 grade 12 students, and it's that at least that means there's more than one way we could satisfy these conditions. Okay, in fact, there are 3 ways, 3 different cases. The fact that there must be at least 3 grade 12 students means there are 3 separate cases which could satisfy them, right? At least 3 means we could have 3 grade 12s and 2 grade 11s because we're choosing 5 total, right? So that's at least 3. But we could also have 4 grade 12s and 1 grade 11. That's still at least 3 grade 12s, right? 4 is at least 3, okay? Or we could even have 5 grade 12s and 0 grade 11s, right? We just can't have 2 grade 12s or 1 grade 12 or 0 grade 12s, but we could have 3, 4, or 5. So that's 3 separate cases to think about. And so what's the total number of possible teams? Well, we could think about, we know how to calculate this, right? How many ways are there to get 3 grade 12s and 2 grade 11s? How many different teams would meet those conditions? Well, it's just there's 20 grade 12s, so 20 choose 3, and then 15 grade 11s, so 15 choose 2, and then multiply those together like we've been doing on those other examples, right? To figure out the total number of ways. We also know how to figure out this with a similar logic, different numbers obviously, but same logic, and we know how to figure out this, right? So we can figure out the number of ways that this team could be put together, or that this team could be put together, or that this team could be put together. So what's the total number of ways that we could do this if we need to have at least 3 grade 12s? Well, add them up, right? The total number of teams is just going to be how many different ways could we make case 1, plus how many ways could we make case 2, plus how many ways could we make case 3. So if we examine those individually, we kind of just talked about it, right? But for case 1, we choose 3 grade 12s from 20 options. So 20 choose 3. And then we have to choose the remaining 2 members of the team from the grade 11s. That has 15 options. So that's 15 choose 2, right? That's how many, that will let us figure out how many different ways we could build the team if it has 3 grade 12s and 2 grade 11s. Multiply them together, that gives us this result. There's 119,700 different teams that have 3 grade 12s and 2 grade 11s if we have this many 12s and 11s to choose from. But we know that we could also choose 4 grade 12s from 20 options. That's 20 choose 4. And 1 grade 11 from 15 options. Whoops, that shouldn't be a 2, that should be a 1. That's a typo, my bad. That should be 15 choose 1. Okay. So we could do, right, 15 choose 1 for that. And then we multiply those together. How many ways to choose the grade 12s? Times, for each one of those, there's 15 ways to choose, or 15 choose 1, which is 15 ways to choose the grade 11. So multiply them together, and that gives us the total number of ways we could build the team if it has 4 grade 12s and one grade 11. And there's one more case, because at least 3, well, that includes all 5 of them being grade 12s. So how many ways are there to choose 5 grade 12s from 20 options? 20 choose 5. You could even, if you're saying, but what about the grade 11s, right? You could actually include them. There's 15 grade 11s, and we're choosing 0 of them. So what do you think 15 choose 0 is? How many ways are there to choose 0 things? Well, there's 1, right? There's 1 way to choose 0 things. You don't choose them, right? You don't pick anything. That's the only way to do it. So 15 choose 0 is 1. When we multiply 1 by 20 choose 5, we still end up with just 20 choose 5, right? And there are 15,504. So how many ways are there total then if we need to have at least 3? Well, how many ways can you have 3 plus how many ways can you have 4 plus how many ways can you have 5? And that gives us the total number of different teams that could be composed of at least 3 grade 11s. Sorry, 3 grade 12s. Now, sometimes there's so many cases, so many different ways we could satisfy our conditions that it actually becomes easier to think about the ones that don't satisfy our conditions. And again, this kind of is similar to what we talked about in the previous lesson, where sometimes it's easier to figure out how many of the arrangements don't meet our conditions and then subtract it from the total number of different arrangements to be left with the ones that do satisfy, right? Again, if we take all of the outcomes that satisfy our conditions and add all the outcomes that don't satisfy our conditions, we should get all of the possible outcomes, right? There's no outcome that could fit into both of these categories. Either it does satisfy the conditions or it doesn't. And if it doesn't, then it doesn't, right? If it does, then it does. It can't be in both at the same time. There's no outcome that belongs to both of these categories. So put them together and we will have described every possible outcome, right? So that means our outcomes that do satisfy our conditions, we can just take all of the possible outcomes and subtract the ones that don't satisfy our conditions, and we'll be left with only the ones that do satisfy. So just to think about why this might be easier, suppose we have the same math team. We're choosing 5 students, okay, from 20 grade 12s and 15 grade 11s. But now the condition is that we must include at least 1 grade 12 student. So we technically could still do this, right? We could say, all right, well, we could have 1 grade 12, 4 grade 11s. That's case 1. Then we could have 2 grade 12s, 3 grade 11s. Or that's case 2. Case 3, 3 12s, 2 11s. Case 4, you get it, right? 4 12s, 1 11, and on, okay? So that is 5 different cases we would have to think about. This will totally work. Don't get me wrong. We could do it. We could take 20 choose 1 and multiply it by 15 choose 4. And then add 20 choose 2 times 15 choose 3. And then add 20 choose 3 times 15 choose 2, and on until we go through all 5 cases, right? Do that, find the number of ways each case could happen, and add them all up. But there's actually a much faster, much easier way, because we could recognize that out of all of the possible ways there are to choose 5 students from a total of 35 students, right? Because that's really how many different ways are there to make this team? Well, there's 35 students, 20 grade 12s and 15 grade 11s, and we're choosing 5 of them. So we could pretty quickly figure out all the different ways to make this team, right? It's just 35 choose 5, okay? And out of all of those different possible ways, there's actually only one case that doesn't meet the conditions. What case is that? We've described everything here except for the one case that doesn't satisfy them. And that's if we choose 0 grade 12s and 5 grade 11s, right? That is the one case where our outcomes, where we would not be satisfying what we need to do for this team. So there are 35 choose 5 total possible ways to choose the team. There are 15 choose 5 ways to choose all 5 of them from grade 11. And that's the number of ways that our condition could not be satisfied, right? So the number of teams with at least 1 grade 12 is going to be the total number of possible teams. Take away the number of teams out of those total possible different ways, take away the number of different ways to make a team with only grade 11s, and what you should be left with is the number of teams with at least one grade 12, right? All the ways to make a team if they have to have more than 0 grade 12s, right? So 35 choose 5, there's 324,632 different ways we could put this team together with no restrictions. And if there's 3,003 ways to choose 5 grade 11s, right? Because again, it's not just, be careful here. I'm not saying there's one way to only choose grade 11s. I'm saying there's one case, right? And there's 3,000 different ways that could still, 3,003 different ways that could still turn out. Okay, but that's one case where we have all grade 11s, right? So 3,003 different ways to just choose grade 11s. So those are all the ways. They're in here somewhere where we don't have any grade 12s. So subtract those off and we're left with the number of different teams that would have at least one grade 12. Cool, right? Okay, so let's try out some examples here. All right, so a university physics student is studying for their midterms. They want to borrow 6 books from the library, which has 8 books on general relativity and 6 books on quantum mechanics. If the student needs at least, okay, so at least right away I'm thinking there might be more than one case that we have to consider. Okay, they need at least 5 general relativity books. How many combinations are possible? Okay, so we need to do 6 total, and we need at least 5 of them to be relativity books. Okay, so can you think of the 2 cases here that could satisfy these conditions? Right, we could pick 5 relativity and 1 quantum mechanics. Or we could pick all 6 relativity and 0 quantum mechanics, right? We have 2 cases, so need at least 5, I'll say GR for short, for general relativity books. Okay, so could have 2 cases, right? There are 2 cases here that could satisfy this. Like we said, we could have 5 general relativity and 1 quantum mechanics, or we could have 6 general relativity, because that's still at least 5, and 0 quantum mechanics books. Okay, so how many ways are there to do this, right? Well, there are 8 general relativity books. So how many ways are there to choose 5 of them? Well, 8 choose 5, right? That's our general relativity. And then how many ways are there to choose 1 quantum mechanics book? Well, there are 6 quantum mechanics books, so there's 6 different ways to choose 1 of them. And we multiply those together, right? So we have 8 choose 5 times 6 choose 1, and that's the total number of ways there are to choose 5 from 8 options and 1 from 6 options, right? To do both of those things. So this is going to be 8 choose 5 is 56, and 6 choose 1 is, of course, 6. So that gives us 336 different ways that we could choose 5 general relativity books and 1 quantum mechanics book, right? 56 ways to choose the GR books, and then 6 ways to choose the QM books. Multiply them together to get the total number of ways to do both things. Choose 5 GR and 1 QM. Okay, but that's not the only way we can satisfy our conditions, because we could have also done 6 general relativity and 0 quantum mechanics, right? So how many ways are there to choose 6 general relativity books? Well, there's 8 options. We're choosing 6 of them. How many ways are there to choose 0 quantum mechanics books? I mean, it's 1, right? Or you could just think of we're not choosing them, so we could just do 8 choose 6, right? This really just becomes how many ways are there to choose the 6 general relativity books? But we can include this still. It still mathematically makes sense because there are 6 books. We're choosing 0 of them, and 6 choose 0. If you do it on your calculator now, you're going to get 1, right? There is only 1 way to choose 0 books. You don't choose any. That's the 1 way. Okay, so 8 choose 6 is 28. 28 different ways to choose the 6 books. 6 choose 0 is 1. only one way to choose 0 books. So that gives us 28 different ways. So what is the total number of possible ways that we could meet these conditions? Well, there's 336 ways to do it that way, and 28 different ways to do it that way. So the total is 336 plus 28, giving us 364 different ways to choose at least 5 general relativity books. All the ways where you have 5 plus all the ways where you have 6 general relativity books gives us the total number of ways to have at least 5 general relativity books. Cool, right? Let's try this one. So, a box of Halloween candy contains 7 chocolate bars and 6 gummy candies. In how many ways can you select groups of 5 candies if at least one must be a chocolate bar? Okay, so if we think about this, right, at least lets us know typically that there's probably going to be multiple ways we could do this, right? Multiple cases to consider. However, if we look here, right, we definitely could do this. At least one chocolate bar. So we could say 1 chocolate, 4 gummies, right? Because we're choosing 5 total. We could do 2 chocolate, 3 gummies. 3 chocolate, 2 gummies, 4, 1, 5, 0, right? That's totally possible. 5 different cases to think about. We would do, 7 choose 1 times 6 choose 4, because there's 7 chocolate bars, 6 gummies, right? And then 7 choose 2 times 6 choose 3, and on and on and on all the way through, and then add those all up. That definitely would work. However, I think there's a faster, easier way to do this, right? What is the one condition that doesn't satisfy? What is the one case, I should say, that doesn't satisfy our conditions? Well, if at least one must be a chocolate bar, there's actually only one case to think about then where we don't have at least one chocolate bar, right? It's just when there's no chocolate and 4 gummies. So our total, right, the total is going to equal the number with 0 chocolates, right, plus the number with at least 1 chocolate. See what I mean, right? All the ways that don't have a chocolate plus all the ways that do have a chocolate gives us the total number of possible ways we could choose 5 candies from this bag, okay? And so we can actually figure out, it's a lot faster to just figure out this one case where we have no chocolates. That's just one case, right? And use that, subtract it from the total to figure out how many will have at least 1. Rather than doing 5 different cases, we can just recognize that there's only one case that doesn't satisfy our conditions. It's this one, right? The number with no chocolate. So that just means, right, thinking about our logic here, we can say that the number with at least 1 chocolate is going to be the total. Take away the ones that don't have any chocolate, right? It equals our total minus the number with 0 chocolate. So our question becomes then, okay, well, how many total ways are there to do this? Well, our total is just going to be, here, I'm just going to work it out up, down here. Total number of ways we could choose 5 candies. Well, how many candies are there to choose from? There's 7 chocolate bars and there's 6 gummies, right? So there's a total of 13 candies, right? 13 candies, and we're choosing 5. How many different total possible ways could that turn out? Well, 1,287, okay? Now we got to figure out how many different ways are there to end up with 0 chocolate. Well, that just means we're choosing all 5 as gummies, right? We're choosing 5 gummies and 0 chocolates. We could look at it like this. So 7 choose 0, that's choosing 0 chocolates. That's just going to be 1 times there's 6 gummies, and we're choosing all 5 of our candies as gummies. So that's going to be, it actually ends up being, this makes sense, 1, right, times 6. there's 6 different ways to choose 5 gummies, right? Essentially, it means there's 6 different ways to leave one gummy behind because there's 6 different gummies. So that makes sense. That's just 1 times 6, or 6. So there's actually only 6 ways we could possibly do it where we choose 0 chocolates. Out of the 1,287 total possible ways to choose the 5 candies, 6 of them involve choosing all gummies and no chocolates. Meaning that, right, so the number with at least one chocolate is going to equal 1,287. That's all the different ways we could choose 5 candies from 13 options. Take away the 6 ways that's included in there of ending up with only gummies. And 1,287 minus 6 is 1,281. So there we go, right? Again, all we did there, think about the one case that doesn't satisfy our conditions, because that's easier than thinking about the 5 cases that do satisfy. This would have worked. You would have gotten the same answer, but you would have done a lot more work to get it, right? Versus just figuring out all the possible ways and then taking out the number of ways that the one case that doesn't satisfy our conditions could turn out. Okay, so go ahead and try this one out. This is a continuation of the one that I asked you to do earlier. Okay, this one contains that keyword at least. So you might have multiple cases to think about here. I think when I did it, I had 3 cases to think about. So try that one out. Figure out the number of ways to do all your different cases and then add them all up to get the total. And when you're finished with that, that actually covers most of the stuff for the lesson. We're just going to look at some more examples, ones where like it's not quite as obvious, at least at first. What are we choosing here? What's the choosing stuff going on? Some of these like word type problems. So when you're finished with that one, come on back and we'll finish up with some of those examples. So let's take a look at this one here. A hockey game ends with handshakes. There were 10 people on the ice and everyone shook hands with each other. How many handshakes were there? So you see what I mean? Like at first, that might be a little tricky to see. How is this, a perm or a combination? But if we think about it, right? What is a handshake? It's really just choosing 2 people out of 10, right? You choose the 2 people, make them shake hands. There you go, right? And we can see the order doesn't matter here, because if I say, person A shakes hands with person B, it's the same handshake as if I say person B shake hands with person A. So the order doesn't really matter here, right? A handshake is just a combination of 2 people. So really what this is asking us is if everyone shook hands, so every possible combination happened, right? Everyone shook hands with each other, then how many handshakes were there is just saying how many ways are there to choose 2 people out of 10 options, right? How many ways are there to make groups of 2 choosing from 10 people, right? So that just means our N is 10. There's 10 people. We know that a handshake involves choosing 2 of them to go together, and we want to know what is then 10 choose 2. That'll tell us how many different handshakes would have happened, because we want to know how many different ways can you group 2 people chosen from 10 options. So 10 choose 2 is 45. 45 handshakes. In order to get every possible pairing of 2 people, from 10 options, you would end up with 45 different pairings and therefore 45 different handshakes. Okay, let's try one from an old diploma, a written response from an old diploma. So this is the other part to a question we saw in the previous lesson. So same information. Students in a math class are creating and exchanging encoded messages with a partner. So given that 630 different pairs of students are possible, we want to algebraically, and that algebraically means representing it with our proper mathematical symbols, right? Algebraically, showing our work, we're going to determine the number of students in the math class. So let's talk about those 2 directing words there, right? Algebraically and determine. Here are the official definitions of those from Alberta Education, right? Algebraically means using mathematical procedures that involve variables or symbols to represent values, right? So essentially showing our work, showing our manipulation of an equation, using the proper symbols, right? You can be docked marks for kind of making up your own symbols, even if the process works out in the end, because part of answering a math question is properly communicating your answer so that people can understand it, right? And determine means find a solution, right? Find the result, find the answer, okay? How? Well, by showing appropriate formulas, procedures, and or calculations. So again, we don't just want to get our answer here. We want to show how we're getting our answer, the algebraic process that underlies it. Okay, so with that in mind, let's think about this one a bit. And for a written response on a diploma, don't be shy to write a little sentence or something to explain what you're doing. It doesn't need to be a full, proper, grammatically perfect sentence or anything, but don't be shy about explaining yourself a bit. If you're ever wondering, oh, okay, is it clear what I'm doing? Words can be a great way to enhance a solution. So I actually probably, if I were a student writing this diploma, I would have probably just quickly said something like, pair is a grouping of two, right? Pair is a grouping of two, right? So that just means, what are we doing here? We're being told that there's 630 different ways that we could create groups of two from however many students are in the class. That's ultimately what we want to figure out, the number of students in the math class, right? So those are the number of options we have. And we're being told we can make 630 different groups of two from those options, right? So this is our n. That's what we need to figure out. How many options were there to choose from? We know that when we make groups of two, when we choose two, we end up with 630 different ways to do it, right? So really what we are doing is we are choosing two from n options. N being the number of students. So if 630, if 630 pairings / combinations are possible, right? That just means that what we know is that n choose 2 equals 630, right? And since, how can we solve for n here? Well, remember, there's a formula for n choose r. N choose r is just n factorial over n minus r factorial, okay? So, now we could say, and since, I guess I just wrote it there, and since NCR equals n factorial over n minus r factorial times r factorial, okay, then we have that 630 equals our n, that's what we're trying to figure out, so I'll leave it as n factorial, over our r is 2, so n minus 2 factorial times 2 factorial. Okay, and now we can go ahead and start actually solving this problem. Okay, you would normally have more room on a written response on a diploma to keep working down the page. I get it though, sometimes you do run out of room. Just make it very clear, very organized, so that someone can still follow your work, right? Something like this to show, okay, I'm done here, I'm gonna move up here and continue solving. Work down the page always. If you need multiple columns, that's okay, but keep it in neat columns that the marker can follow. Okay, so let's work on now, how can we actually solve for n? We know that 630 equals, again, n factorial over n minus 2 factorial times 2 factorial. But hang on a sec. N minus 2 factorial, remember, whenever working with factorials, pretty much always the strategy we're going to use is, well, we need to get rid of those factorials, right? We can't really algebraically analyze this if we don't know what n is. We certainly don't know what n times every integer that's below it is, but we can get rid of those factorials by noticing that, hey, n minus 2 factorial is kind of contained within n factorial, right? Because all a factorial is you multiply it by, subtract 1 and multiply that, and then subtract 1 and multiply that, right? 7 times 6 times 5 times 4, for example. So same idea here. What is n factorial? Well, it's n times whatever's 1 below n times whatever's 2 below n, and on and on. And I'm going to choose to stop there because after that, it just becomes n minus 2 times n minus 3 times n minus 4, which is just n minus 2 factorial, right? N minus 2 times the thing that's 1 below it times the thing that's 1 below that. So this is just n minus 2 factorial from then on. And I'm stopping there because I see that there's an n minus 2 factorial in my denominator. In fact, while we're here, 2 factorial is just 2 times 1, so we can just change that to 2. And then look at this. N minus 2 factorial over n minus 2 factorial is just 1. We don't know what n is, but we know that n minus 2 factorial over n minus 2 factorial is a number over itself, and that always equals 1. So we've got 630 is equal to n times n minus 1 over 2. And now, doesn't this look like we're kind of back in Math 20, solving a quadratic equation, right? Well, we are. This is exactly that, okay? So if I go ahead and I'm solving for n, I'm going to first just multiply both sides by 2 to get rid of that division by 2. That's going to give us 2 times 630 is 1,260. Okay, so 1,260 equals n times n minus 1. It's starting to look more like a quadratic. Now, I will say here, okay, I mean, it's not starting to look like a quadratic. It is a quadratic, but it's starting to look like one of our usual polynomial or trinomial ones, okay, if we were to expand this out. I will say here, there's something to be said for these. Sometimes you can get like big numbers here that can be hard to think about factoring. Not impossible by any stretch, okay? But what you can kind of make use of, if you were writing this diploma, what you could say is just a quick note, like something like, so 2 consecutive integers, because that's what these are, right? N times n minus 1, well, this is something, and this is just a number that's 1 below it, right? It could be 8 times 7 or 9 times 8 or something like that. 2 consecutive integers that multiply to 1260. And that's not actually that hard to do. Typically, we don't do this with quadratics because it's kind of hard to think of, right? But the fact that they're consecutive means we can kind of just like try stuff. Like we know roughly 1,260, like we could say, well, 20 times 20 is only 400, so it must be bigger than 20. 30 times 30 is 900, so it must be, it's not 30 and 31. 40 times 40 would be 1,600, so we must be somewhere between 30 and 40. And then we could try, okay, so is this 32 times 31, 33 times 32, 34 times 33, right? So you could get away with that. You could explain yourself and say, we're just looking for 2 consecutive integers that multiply to 1,260. Explain some stuff like, 30 times 31 is, what is that? That's 930. Right? And say, so we need something larger, maybe 31 times 32, see what that is. That's an acceptable algebraic process here. We're kind of just using logic. Now, we could also just go at this fully as a quadratic, which is probably what I'll do here. Notice that we've got 1,260. If I expand this out, I get n squared minus n. And then, like solving any quadratic, it's going to be a lot easier if we have like stuff equals 0, because then we can just factor and set each factor equal to 0 to find our solutions. So I'm going to subtract 1,260 from both sides to get this. And this is what I was referring to. Sometimes these can be a little tricky. We need 2 numbers that multiply to negative 1,260 and add to negative 1. Makes sense because they're 2 consecutive numbers, right? So when we add them, they should be separated by 1, okay? So let's think about this. 2 numbers that multiply to negative 1,260. Definitely a little tough to think about, but we could try a few, and what we'll end up with, right? Like I said, you can kind of gauge roughly where you're at. You know they can only be separated by 1. One's positive, one's negative, because when you add them, you just get negative 1. So you could use that logic of, well, 30 times 30 is only 900. 40 times 40 is 600. So the answer is somewhere between 30 and 40, right, to give us negative 1,260. It's actually right smack dab in the middle. The 2 numbers that multiply to 1,260 and add to negative 1 are actually negative 36 and positive 35. So those tell us our 2 factors, meaning that we've got n minus 36 is 1 factor, and then n plus 35 is the other factor. Okay, and those two factors equal 0 when we multiply them together. Now, if we're multiplying two things together and the answer needs to be 0, that's only possible if this is 0. So that is one possible solution. One value of n that could make this equation true is the one that makes n minus 36 equal 0, which of course is just 36. But we have another solution condition here. This could also be true if n plus 35 were to equal 0, and therefore if n were to equal negative 35. So we get two solutions to this quadratic equation. However, do both of them make sense? Don't forget what we were trying to figure out here, right? We were trying to figure out the number of students in the math class. Can a math class have negative 35 students? No, right? So while it solves the equation, we did nothing wrong in finding it. We have to reject it because it doesn't make sense. In fact, that's the case even if this, even if it wasn't students. Anytime you're dealing with a combination, you can't have a negative n. It just doesn't make sense. This represents the number of options to choose from. You can never have negative options for anything, whether it's letters in a word or numbers in a license plate or students in a class. There's no such thing as negative options to choose from. So whenever dealing with these, n can never be negative, right? So this is an extraneous solution. If I were writing the diploma, I would probably explain we can't have negative students. So this is extraneous. Right? That's an extraneous solution. This one's fine. We can have 36 students. In fact, they do. So there are 36 students in the class. On a diploma, I would definitely give a little statement just to show that I understand what my answer means, right? That it represents the number of students in the class, and that I get what we've just found, okay? And there we go, there's that one. So another one straight from a diploma, this time a multiple choice, not a written response, but let's just read the question first so we know what to look for. The number of polygons that can be created that have at most 4 sides. Ooh, at most, okay, sounds like we might have multiple cases. Let's just see what's happening here. A circle is drawn with 6 points on its circumference, as shown in the diagram below. So circle, 1, 2, 3, 4, 5, 6. A student creates polygons. Remember what a polygon is, right? For example, like a square or a rectangle, those are polygons. A triangle is a polygon. It's just a closed shape, meaning it has to be closed. So that's not a polygon because it's not closed, right? It's open, okay? Has to have straight closed sides. So a circle is not a polygon either because it doesn't have straight sides. But anyway, the student is creating polygons with 3 or more sides by connecting the points with straight lines. We want to know how many polygons could be made that have at most 4 sides. So what is this talking about? Let's think about it, okay? So if I connect the points with straight lines, because polygons are made up of straight lines on their borders, right? Like I could make that triangle, right? Or if I choose 3 different points to connect, maybe these 3, well, one's the same, but 2 are different, right? Or if I choose these 3, aha! Whoops, that's not a very straight line, but you see what we're doing, right? To make those different triangles, I just chose different points to connect. And then I could try, making these ones. So notice what I'm saying there, right? I'm choosing 3 points to connect, and that makes a triangle, right? If I connect 4 points, 1, 2, 3, 4, right? I chose those 4, so I made a quadrilateral, right? A 4-sided polygon is called a quadrilateral, okay? And again, that's all we're doing. If I connect 4 different points, if I choose 4 different points that I'm going to connect, I've made a different 4-sided polygon, okay? So all we're doing here, to make an n-sided polygon, we're just choosing n dots to connect, right? Or I guess I should say r. Creating an r-sided polygon and you wouldn't have to explain this and write it on a multiple choice on a diploma. No one's going to look at your multiple choice. But just so, since I'm teaching it so we can follow the logic here, right? Creating an r-sided polygon just means choosing r sides to connect, right? So again, for example, if I connect not r sides, r points to connect, right? If I want to make a three-sided polygon, I could connect these 3 points, right? If I wanted to make a different three-sided polygon, I could connect these 3 points. If I wanted to make a four-sided polygon, how many points would I connect? 1, 2, 3, 4. If I wanted to make a five-sided polygon, what would I do? I would choose 5 points to connect. So maybe 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5. There we go. I counted wrong, right? That makes a pentagon, a 5-sided polygon. Okay, so that's all we're really doing. To make an r-sided polygon, we choose r points and connect them. Okay, so we have 6 points to choose from. We have 6 points to choose from. So therefore, our n is just 6, right? And we will choose r sides. So really what we're doing here is just 6 choose r, and that will tell us how many ways are there to make an r-sided polygon. Now we were asked about the number of polygons that can be created that have at most 4 sides. So that means we don't want to include 5-sided polygons and we don't want to include 6-sided polygons. So we're not going to do 6 choose 5 and we're not going to do 6 choose 4. Okay, but as we've seen, we can do 6 choose 3 and we can do 6 choose 4. What about less than 3? Could we do a 2-sided polygon? If you think about it, can you make a 2-sided polygon? Is there a way to connect 2 points and actually make a polygon? There's not, right? Because a polygon has to be made up of straight lines and closed. That's just a line. That's a line segment. So if it asked how many ways are there to create line segments, we could do 6 choose 2, but a line segment is not a polygon, right? So there's just these 2, right? It's 2 cases to think about. So we can say case 1 is choosing 3 points to connect, right? That's making 3-sided polygons. We want to figure out how many different triangles can we make, essentially, right? So that's just going to be, well, like we said, 6 choose 3. 6 to choose from, and we are choosing 3 of them to connect in order to make a 3-sided polygon, a triangle. And 6 choose 3 is 20. Okay, now case 2 is choosing 4 points to connect, right? Making 4-sided polygons, quadrilaterals, right? How many different quadrilaterals can we make? Well, that's just 6 choose 2. Sorry, not 6 choose 2, 6 choose 4. I don't know where I got 2 from. I think I looked at case 2 there. I think that's what made me say 2. So 6 choose 4 is 15, right? And notice they pick the distractors to try and get you, right? At most 4. That's more than one thing, right? That's could be 3, could be 4, right? Those are both 4 at most. So we have to include both of them. If there's 20 different triangles we could make, and then 15 different quadrilaterals we could make, well then in total, there's 35 different polygons we could draw that have at most 4 sides, right? So be careful. If we had just done 6 choose 4, we would have chosen A, right? That's why that's there. They don't just make up random numbers. They do it based on common student mistakes. So the total number of 3 or 4-sided polygons we could make is 20 plus 15, or 35. Option D. All right, one more thing to talk about here, and then we are finished. So the last thing here is when we have combinations and permutations. It's usually like a combination within a permutation or vice versa, right? So sometimes we need to first choose from a group, and the order we choose them doesn't really matter. But then we need to arrange the objects for which the order does matter, right? So essentially what we're going to do is, well, we'll use combinations to choose the items, and then we'll use permutations to arrange them. Basically what we're doing is figuring out how many ways there are to even choose the groups of R objects in the first place, right? If we're given, we need to, figure out how many ways there are to arrange, a certain number of choices. Well, first we need to figure out how many different ways could we even make our choice in the first place. Then we can worry about how many ways are there to arrange them, right? So since each different set of R items chosen will have R factorial ways of being arranged, we'll just need to multiply the number of combinations by the number of permutations, right? Again, all the different ways that we could choose the R items in the first place, where order doesn't matter, for every single one of them, they will then have R factorial ways of being arranged. Okay, so that's why we're going to multiply them together. So let's try this out. Let's see what it looks like. From the letters in the word Camrose, how many different arrangements of letters can be created from 3 consonants and 2 vowels? So do you see what I mean here, right? We have to figure out, okay, well, first of all, there's a lot of different ways we could choose 3 consonants and 2 vowels, right? Like we could go CMR, but we could also go CMS, or we could go MRS, right? So there's a lot of different ways to even just choose the consonants in the first place, as well as the vowels, right? The vowels, we could do AO, AE, or OE, right? Now the order we choose them doesn't matter, right? We're just trying to decide what letters make it into our word in the first place. But there are still many different ways that we could decide what letters make it into the word in the first place, okay? So that's essentially, we can look at it like this, right? So let's just we'll use combinations to find number of ways to choose 3 consonants and 2 vowels. Okay? Because there are many ways to do that. That's not even getting into how many ways we can then arrange them once they're chosen. There's multiple ways to even just choose them in the first place. So for our consonants, there are how many? CMRS. So 4 consonants, right? And we're going to choose 3 of them. 4 choose 3, unsurprisingly, is 4. Right? If we're choosing 3 out of 4 options, there's 4 different ways to do it, because think of it this way, right? There's 4 things, we're choosing 3 of them, so 1 is left behind, right? The 4 different ways are just leaving one of the 4 behind, right? Leaving a different one behind, giving us 4 different ways to choose 3 things from 4 options. Now, what about the vowels? How many ways can we choose our vowels? Well, there's 3 vowels, A, O, and E. So there's 3 vowels to choose from. We're going to choose 2 of them. Similar logic here. That means there are 3 ways to choose the vowels. So be careful, we're not done yet, right? How many ways then are there to choose 3 consonants and choose 2 vowels? Well, 4 ways to choose the consonants, and for each of those, there's 3 ways we could match them up with some vowels. So overall, there are 4 times 3 ways to choose the consonants and the vowels, right? In other words, 12 ways to choose 3 consonants and 2 vowels. Okay, but now we've got to think about, all right, how many different arrangements could we then do, right? So there's 12 ways just to pick the letters, and for each of those, we could now arrange them in many different ways. Okay, so in step 2 now, we'll use permutations to determine how many ways 5 letters can be arranged. right? I mean, we could say it's 5 permute 5, but we also know it's just 5 factorial. 5 times 4 times 3 times 2 times 1. 5 letters could go in the first spot, 4 in the second, 3 in the third, 3 in the third, 2 in the fourth, and 1 in the fifth spot, right? It's just 5 factorial. 5 times 4 times 3 times 2 times 1, which is 120. So if we have 5 letters, there are 120 different ways we could arrange them, right? But there's 12 ways to even just get our 5 letters in the first place. For all 12 of them, there's 120 ways they could be arranged, right? 5 letters, 5 different letters can come out 12 different ways. And then for every single one of those 12 ways, the 5 letters can be arranged in 120 different arrangements. So we could say step 3, for each of the 12 ways the letters can be chosen, they can be arranged. The 12 ways 5 letters can be chosen. They can be arranged 5 factorial or 120 different ways. So we need to multiply 12 by 5 factorial, right? So 12 times 120, that's 5 factorial, gives us 1,440 possible arrangements, possible different ways that we could arrange 3 consonants and 2 vowels from the word Camrose, right? 12 ways to even choose the 3 consonants and the 2 vowels in the first place. And then for every single one of those, there's 120 ways to actually rearrange those 5 letters that we chose, giving us that as our final answer. Okay, last one here. Okay, so there are 5 different physics textbooks, 2 different chemistry textbooks, and 2 different biology textbooks on a library cart. How many different ways are there to arrange 2 physics textbooks, 2 chemistry textbooks, and a bio textbook? So arrange is the key, well, one of the key words there, right? We are going to have to think about the order, but also we can recognize, hey, there's actually a lot of ways to even select the books in the first place, right? 2 physics textbooks chosen out of 5, there's a lot of ways to just choose our 2 physics textbooks, right? Chemistry, okay, not so much because there's only 2 books and we're picking both of them, but bio, right? There's a lot of 2 ways that we could choose 1 bio book out of 2 options. So before we start thinking about how many different ways can we arrange the books that we choose, we kind of have to think about, well, how many ways can we even just choose the books, right? Then we can worry about, all right, now for each of those, how many ways could they be ordered, okay? So kind of went ahead a bit here and wrote this out, but first we're going to use combinations to find the ways that we can even select these groups of books, right? So for physics, there are 5 options, right? 5 different physics textbooks. So we're going to choose 2 of them to put on the shelf. How many ways can we do that? Well, 5 choose 2, right? Which is 10. And then for chemistry, well, this makes sense. There's only 2 chem books. We're choosing both of them, right? 2 chemistry textbooks. So 2 choose 2. There's only one way to do that. You got to pick both of them, right? No way around it. Bio, again, kind of makes sense. We want to choose 1 biology textbook. There are 2 to choose from. So there are 2 ways to choose 1 book from 2 options, right? You can choose book A or you can choose book B. Those are the 2 ways, right? Now, overall, what does that mean for how many ways our books can be selected though, right? Fundamental counting principle comes into play here. Because yes, there's 10 ways to choose our physics books, but for each of those 10 ways, we could choose 1 bio book or we could choose the other bio book, right? Chemistry doesn't really add too much to the number of different ways because there's only 1 way to choose 2 out of 2. So our total number of arrangements is 10 times 1 times 2 or 20, right? There's 20 different ways to even select the books. And now we can think, okay, but for each of those 20 ways, how many ways could the books be arranged, right? Because 20 different ways to select our books, and then for all of them, we could arrange them in, well, how many books are there? 2 physics, 2 chemistry, and 1 bio. So that's 2 plus 2 plus 1, 5 books, right? Now we can use perms to think about how many ways there are to arrange whatever 5 books we choose. So for all of the different combinations of books we can pick, we can arrange each of those in 5 factorial ways, or 120, right? So we can pick 5 books in 20 different ways following these conditions. And then for all of those 20 different ways, we can arrange those 5 books in 120 ways, right? So again, for each of the 20 ways to select the books, to select 5 books, the books can be arranged. And this is definitely wordier than you would probably be when working out your practice problems, right? But I'm just really showing my thought process here as we go through this example so you can hopefully follow the logic. The books can be arranged 5 factorial ways, right? So if there's 20 ways to do it, and for each of them we can arrange it in 120 different ways, then we need to do 20 times 120, 20 times 5 factorial, right? Giving us 2,400, whoops, that's too many zeros, 2,400 possible arrangements that meet these conditions. So if we want to arrange, we want to know how many different ways can we arrange 2 physics chosen from 5 options, 2 chemistry chosen from 2 options, and 1 bio chosen from 2 options. There's 2,400 possible different ways that we could end up with those books on our shelf when order matters for the 5 chosen ones. And now that we've done that, I just want to really quickly revisit that one from the previous lesson. Remember the student who got 2 out of 2 on this written response question, right? And I kind of mentioned in the previous lesson, like, okay, she's using combinations, which I know we haven't talked about yet, or they're using combinations, which I know we haven't talked about yet, but we can still solve this problem with permutations as well, like we did in the previous lesson. Well, now that we've done combinations, let's revisit it and just see how there's multiple approaches you can take and how their approach actually makes a ton of sense here. So a student is asked to encode the word factor, just reminding ourselves of what this question was, by replacing each letter of the word with a different math symbol. There's 10 math symbols available. The student creates a key, a list of his letter symbol replacements, and gives it to his partner. Okay, so essentially it's saying how many different ways could you represent the letters in the word factor if you have 10 symbols to choose from, right? And so how this student chose to approach it was they did what we kind of just did on these examples. They said, well, first, we need 6 symbols, right? And there's 10 to choose from. So how many ways could we choose 6 symbols from 10 options? And they're thinking, all right, well, first let's just figure out how many ways we could decide on our symbols in the first place. Then we can worry about assigning them to each letter. That's where order will matter. But for first choosing them, right, they say there's 10 math symbols to choose from, 6 letters in the word factor. Therefore, we need to pick 6 symbols, right? Now, since at this point they're thinking of it as we're just choosing the 6 symbols from 10, the order doesn't really matter yet. We're just saying how many different ways could we decide which 6 symbols we're going to use, okay? And how many ways are there to choose 6 items out of 10? Well, 10 choose 6. Now, after choosing those 6 symbols, right, that's where order is going to come into play, because now we actually have to think, okay, how we're ordering them is really assigning them to a letter in factor, right? So just, it said math symbols, so maybe these 6 symbols are what we end up choosing. Rearranging them assigns them to a different letter in factor, right? If I wrote it like this instead, right, that now gives me a different code. So that is where order starts to matter. Right? So what this student has said is there are 10 choose 6 ways to even decide what 6 symbols we're taking from the 10 options. Now we have to think about arranging them to represent a letter in the word factor. Because each letter is unique, the order they arrange them matters, right? So this student is talking about, they're explaining, they're doing that key word, explain, right? Why does order matter now? Why are we switching from combinations to permutations? And they've done a good job here, right? 2 out of 2 on this one for them. So they'll arrange the 6 symbols so that each one matches a letter. To find the possible arrangements for 6 items, they chose to do 6 permute 6. They also could have just said 6 factorial, right? Because they need to choose the letters and arrange them, they multiply the number of possible outcomes for the 2 together, right? 10 choose 6 ways to even decide on our 6 symbols, and then permute 6 ways to figure out the different orders and therefore let them represent different letters, okay? And so they multiply them together to get the final answer of 151,200. And then a nice little statement explaining what their answer represents, right? Showing that they understand what this actually means and how it is the answer to the question they were asked, okay? So just wanted to revisit that one now that we've talked about, combinations and how we could have actually applied them in that lesson from the previous lesson, okay? Didn't have to. It was totally solvable with just permutations as well, but there's often more than one way to think about this stuff. That's what's fun about math. Okay, anyway, that wraps up the notes for this one. So these are my suggested practice questions at this time while it's fresh in your brain, but you can do the rest of the practice now, whatever you've got left to do, okay, to gain comfort with this stuff and see what you might need some more practice with or what you might want to reach out for questions with. Don't be shy to hesitate, or don't be shy, don't hesitate to reach out if you do have questions. I'm always happy to help. But there we go, that wraps that up. So we only have one more lesson in Math 30-1 after this. Hard to believe.